Section: Introduction. In this section, we delve into the realm of training data attribution (TDA) techniques. Our aim is to grasp how training data influences the characteristics of trained models. TDA methods play a crucial role in pinpointing data points that have a significant impact on a model's predictions. This insight is invaluable for interpreting, debugging, and enhancing models. These techniques find applications in various areas of machine learning, such as spotting mislabeled data points, creating data poisoning attacks, and managing datasets. Many TDA methods strive to make counterfactual predictions. These predictions estimate how a trained model's behavior would alter if specific data points were removed from or added to the training dataset. Unlike sampling-based approaches that require repetitive model retraining with different data subsets, gradient-based TDA techniques estimate a tiny version of the counterfactual without retraining the model. There are two main strategies for gradient-based counterfactual TDA: implicit differentiation and unrolled differentiation. Implicit differentiation-based TDA, notably influence functions, uses the implicit function theorem to gauge how sensitive the optimal solution is to downweighting a training data point. These methods work well for models with strongly convex objectives and offer convenient estimation algorithms that rely solely on the optimal model parameters. However, they are limited by assumptions like the uniqueness and convergence to the optimal solution, restricting their applicability to modern neural networks. On the other hand, unrolling-based TDA, such as SGD influence, approximates the impact of downweighting a data point's gradient update on the final model parameters by backpropagating through previous optimization steps. Unrolling is appealing for modern neural networks as it does not depend on the uniqueness or convergence to the optimal solution. It can also consider details of the training process, like the choice of optimizer and learning rate schedules. In our work, we bridge the gap between implicit differentiation-based and unrolling-based approaches by introducing a novel algorithm that combines the strengths of both methods. Our method, named source segmented stationary unrolling for counterfactual estimation, divides the training trajectory into segments and approximates the distributions of gradients and Hessians as stationary within each segment. Source inherits advantages from unrolling, such as attributing data points at different training stages and incorporating algorithmic choices into the analysis. We evaluate source across various tasks, including regression, image classification, text classification, and language modeling. Our method surpasses existing TDA techniques in approximating the impact of retraining the network without specific data point groups and identifying training data points that would alter predictions on some test examples if trained without them. Source excels in scenarios where traditional implicit differentiation-based methods struggle, like models that have not fully converged or those trained in multiple stages. Our empirical findings highlight source as a valuable TDA tool in diverse scenarios. Section Summary. In this section, we introduce training data attribution (TDA) techniques that aim to understand the relationship between training data and model properties. These methods, such as implicit differentiation and unrolling, help identify influential data points without requiring repeated model retraining. Our novel algorithm, source, combines the advantages of both implicit differentiation-based and unrolling-based approaches, offering a comprehensive framework for TDA that can analyze data points at different training stages and incorporate algorithmic choices, outperforming existing methods in various tasks. Section: Training data attribution. In this section, we aim to explain how models behave on specific data points by referencing the data used during training. We typically quantify model behavior using a chosen measurement, such as loss or margin, based on the analysis metrics. An attribution method assigns a score to each training data point to show its importance in influencing the model's behavior on a given data point. One method, called Leave One Out, LOO, retraining, evaluates a data point's importance by analyzing how excluding it from the training set affects the model's performance. A higher LOO score indicates a more significant change in the model's performance when that data point is removed. However, LU retraining can be computationally intensive as it requires retraining the model for each data point, making it impractical for large models and datasets. Influence functions estimate how optimal parameters change when there is a small change in the weight of a training example. They approximate this change using a mathematical formula involving the Hessian of the cost function and the Jacobian of the response function. Influence functions provide algorithms that rely only on the optimal parameters but may not accurately reflect real-world scenarios, especially in neural networks. They are limited in their ability to analyze the effect of removing a data point at different stages of training or in multi-stage training procedures. Section Summary. In this section, we delve into training data attribution, TDA, which aims to explain a model's behavior on a specific data point by referencing the data used during training. TDA quantifies model behavior using a chosen measurement and assigns important scores to training data points based on their influence on the model's expected output. Additionally, we explore influence functions, which estimate how optimal parameters change with small perturbations in training data weights, providing insights into the impact of removing specific data points on model performance. Section: Evaluation of TDA techniques. In this section, we evaluate TDA techniques. We often use LU estimates as a benchmark for assessing these methods due to their focus on counterfactual prediction. However, calculating LU scores in neural networks presents various challenges, as explained in the appendix. To provide a more reliable evaluation measure for TDA techniques, we utilize the Linear Data Modeling Score, LDS, and subset removal counterfactual evaluation. The Linear Data Modeling Score, LDS, is a score assigned by a TDA method to each pair of a query and training data point. By summing the scores of individual data points within a specific training subset, we can estimate the subset's impact on a measurable quantity, denoted as F. The LDS for a query point, bold symbol Z_Q, is determined based on a hyperparameter configuration, bold symbol lambda, and Spearman correlation, bold symbol rho. We approximate the expected measurable quantity by retraining the network multiple times under different random choices and then average the scores across numerous query data points to obtain the final LDS. Subset removal counterfactual evaluation involves analyzing the change in model behavior when highly ranked data points are removed. For classification tasks, we assess if removing the top k positively influential data points leads to misclassification on average. This evaluation method directly measures the effectiveness of TDA techniques in identifying data points that significantly impact the model's behavior. Furthermore, TDA techniques are also assessed based on their performance in downstream tasks like detecting mislabeled data, class detection, identifying hallucinations in the training dataset, and extracting factual knowledge from the training data. These tasks provide additional insights into the practical applicability of data attribution methods. However, the relationship between these tasks and counterfactual prediction is often unclear, and it remains uncertain whether enhancements in counterfactual prediction algorithms will directly enhance performance in these downstream tasks. Lastly, we introduce source, segmented stationary unrolling for counterfactual estimation, in this section. Source is a gradient-based TDA technique that combines implicit differentiation and unrolled differentiation advantages. By leveraging suitable approximations, we develop an influence function-like estimation algorithm and implement a practical version of source by approximating the Hessian using the eigenvalue-corrected Kronecker-factored approximate curvature (EK-FAC) parameterization. Section Summary. In this section, we evaluate TDA techniques by introducing the Linear Data Modeling Score, LDS, as a robust measure for assessing these methods. The LDS calculates the importance of specific training data subsets on the model's measurable quantity by attributing scores to individual data points within the subset. Additionally, we explore subset removal counterfactual evaluation, which analyzes the impact of removing highly ranked data points on model behavior, providing a direct measure of TDA techniques' effectiveness in identifying influential data points. Section: Motivation. Unrolling for training data attribution. In this section, we aim to optimize our model parameters using stochastic gradient descent, SGD, with a fixed batch size B, starting from the initial parameters, bold symbol, theta, _0. At each iteration, we update the model parameters using a specific rule that depends on the learning rate, eta_k, and mini-batch of examples, B_k, randomly selected from the training dataset D, the data point, bold symbol, Z_key, within the mini-batch, and the total number of iterations T. Our goal is to investigate the impact of removing a specific training data point, bold symbol, Z_m from D on the final model parameters, bold symbol, theta_t. We represent the weight of bold symbol, Z_m as 1 plus epsilon, where epsilon ranges from -1 to 1. When epsilon equals 0, it corresponds to the original training run, and when epsilon equals -1, it means removing the data point. This representation leads to a particular update rule involving an indicator function. To simplify the analysis, we approximate the change in the final parameters due to data removal with a first-order Taylor approximation. This approximation involves calculating the derivative of bold symbol theta_t with respect to epsilon at epsilon equals 0. By differentiating through the unrolled computation graph for the training process, we can evaluate this total derivative. We define delta_k as the number of times bold symbol Z_m is chosen in batch B_k. Using the chain rule of derivatives, we can determine the contribution of each iteration k to the total derivative by multiplying the Jacobian matrices along the accumulation path. This calculation involves the mini-batch Hessian h_k for iteration k and other defined terms. The unrolling-based approach we use for training data attribution, TDA, offers advantages compared to other methods like influence functions. It does not rely on assumptions of uniqueness or convergence to the optimal solution. This method allows us to estimate the sensitivity of the final model parameters to downweighting a data point, considering various aspects of the training process. To ensure stability and reliability, we consider the expectation over multiple training trajectories rather than focusing on individual trajectories. We are interested in the average treatment effect resulting from removing bold symbol Z_m, which we approximate by the negative expectation of the derivative. This expected total derivative can be expanded as a sum over all iterations, leveraging the linearity of expectation. While we could use a Monte Carlo estimation approach by averaging numerous training trajectories, it is computationally expensive and may require a large number of samples for accurate estimates. Section Summary. In this section, we explore the impact of removing a specific training data point on the final model parameters by parameterizing the weight of the data point. By utilizing unrolling-based training data attribution, TDA, we estimate the sensitivity of the terminal model parameters to downweighting a data point, considering details like learning rate schedules and optimizer biases. Unlike implicit differentiation methods, unrolling in TDA allows for a more detailed understanding of how removing a data point affects the training process and final model outcomes. Section: Segmenting the training trajectory. In this section, we segment the training trajectory to develop a more efficient algorithm for approximating the derivative of theta with respect to epsilon. We divide the training process into L segments to simplify the reverse accumulation computations for each segment using statistical summaries. The reasons for segmenting the training process are twofold. Firstly, the training may involve multiple stages with different goals or datasets, such as in continual learning or foundation models. Secondly, the Hessians and gradients change significantly during training, so segmenting allows us to treat their distributions as constant within a segment. We label the segments as L equals 1 to L, with boundaries T_L. By convention, T_L is the end of training and T_0 is the start, while K_L represents the total iterations within a segment. We compute the total derivative using reverse accumulation over a coarse-grained graph in terms of segments. The Jacobian for each segment is denoted as S_L equals J_T_ELL1 T_L. To estimate the expected total derivative, we rewrite the equation using segment notation and assume independence of Jacobians across segments. To make tractable approximations for E_S_L and E_R_L, we assume the Hessian and gradients distributions remain constant within each segment. This means the Hessians share a common mean bar H_L and gradients share a common mean bar G_L within a segment. We also approximate the step sizes within each segment with their mean bar eta_L. If these approximations are inaccurate due to rapid changes in Hessian and/or gradients, dividing the trajectory into more segments can improve accuracy at the cost of increased computation. We further approximate E_R_L in the final equation using stationary and independence approximations. The behavior of f_r can be described by the function f_erm_inv, sigma equals 1 sigma plus lambda, where lambda equals bar eta caret minus 1 _lk _l caret minus 1. This approximation leads to expressing EQ_xb_ approximately as bar h_l plus lambda I caret minus 1 bar g_l, which resembles the formula for influence functions but with expected Hessian and gradient values. This analysis provides a formula for the damping parameter lambda, eliminating the need for manual tuning. Influence functions can be seen as a special case with a single segment, and our approach offers an alternative rationale for them. Section Summary. In this section, we segment the training trajectory into multiple parts to efficiently approximate the derivative of the training objective with respect to a hyperparameter. By dividing the training into segments, we can treat the Hessians and gradients as stationary within each segment, simplifying the computation. This segmentation approach allows us to approximate the total derivative using reverse accumulation over coarse-grained computation graphs, enabling us to handle evolving distributions of Hessians and gradients during training more effectively. Section: Full Procedure. In this section, we present the full procedure. We have developed a method to estimate the expected total derivative in a closed-form expression. This estimation takes into account the impact of downweighting a data point during training. Our algorithm, called source, segmented stationary unrolling for counterfactual estimation, incorporates detailed information about optimization trajectories, similar to the unrolling technique. Source is versatile and can handle various scenarios. For example, it can analyze non-converged models by considering the total number of training iterations. It can also analyze multi-stage training setups, where the model is trained sequentially on different datasets. In such cases, source can calculate the contribution of a data point from a specific dataset segment. To estimate the change in a measurable quantity when removing a training data point, we introduce a single training run estimator for source. This estimator does not require knowledge of the exact location where the data point was used during training, as it focuses on the overall effect within a segment. To address other sources of randomness, such as model initialization, we propose a multiple training run estimator that averages results from different training runs. Next, we outline a practical algorithm for implementing source. We organize model checkpoints into distinct segments and estimate the stationary Hessian and gradient within each segment. To handle neural networks' computational challenges, we use a parametric approximation called Eigenvalue-Corrected Kronecker-Factored Approximate Curvature, EK-FAC, to approximate the Hessian. This approximation simplifies the computation of key quantities in our method. Section Summary. In this section, we present a closed-form term to estimate the expected total derivative in our algorithm, source, which leverages segmented stationary unrolling for counterfactual estimation. Source can incorporate detailed information about optimization trajectories, supporting scenarios like non-converged models and multi-stage training pipelines. By organizing model checkpoints into distinct segments and estimating stationary Hessian and gradient within each segment, Source provides a practical approach for approximating the impact of removing a training data point without needing exact data point locations during training. Section: Computation Costs. In this section, we compare the computation costs of our method, Source, with influence functions using the ek-fac approximation. To perform TDA on all segments, Source requires computing the ek-fac factors and training gradients for each model checkpoint, making it more computationally expensive by a factor of the number of checkpoints. However, when TDA is only performed on a specific segment, we only need to compute training gradients for the relevant checkpoints within that segment. In our approach, AVG_params, we present a more computationally efficient version of Source. Here, instead of averaging Hessians and gradients, we average the parameters within a segment. This variant of Source is more computationally expensive than influence functions by a factor of L, as the ek-fac factors and gradients only need to be computed once for each segment. Furthermore, our method, Source, can be combined with other approximation techniques like TRAC and DATAINF for implicit differentiation-based TDA methods. For instance, we can use random projection as in TRAC to efficiently compute averaged Hessians and gradients in a lower dimensional space. TRAC is particularly useful when dealing with many query data points, as it stores compressed training gradients in memory to avoid recomputing them for each query. In the realm of modern TDA techniques for neural networks, approaches can be broadly categorized into sampling-based, representation-based, and gradient-based methods. Sampling-based methods involve retraining models on different data subsets to approximate counterfactuals, which can be computationally intensive. Representation-based techniques evaluate relevance by comparing the similarity of data points in a representation space, offering computational advantages as they only require forward passes through the network. Gradient-based TDA methods involve implicit differentiation and unrolling strategies, with varying applicability to different model sizes and training scenarios. Overall, our method, Source, offers a computationally efficient approach for TDA in neural networks, with the flexibility to integrate with various approximation techniques for improved performance in different scenarios. Section Summary. In this section, we discuss the computation costs of the Source method compared to influence functions with the same ek-fac approximation. Source is computationally more expensive, requiring the computation of ek-fac factors and training gradients for each model checkpoint when performing TDA on all segments. Additionally, we introduce a more efficient version of Source in AVG_params, where parameters are averaged within a segment instead of averaging Hessians and gradients, making it less computationally expensive. Section: Experiments. In this section, we explore two main questions through our experiments. First, we compare Source with existing TDA techniques using the Linear Data Modeling Score, LDS, and subset removal counterfactual evaluation. Second, we investigate if Source can help with data attribution in cases where implicit differentiation-based methods struggle, especially with models that have not converged or have been trained in multiple stages with different datasets. Our experiments cover various machine learning tasks such as regression, image classification, text classification, and language modeling. We compare Source with TDA techniques like representation similarity, REPSIM, TRACIN, TRAC, and influence functions, IF, with the ek-fac approximation. We define the measurement as the margin for classification tasks, absolute error for regression tasks, and loss for language modeling. We conduct evaluations in two settings. In the first setting, TDA techniques use model checkpoints from a single training run. Source uses 3 segments equally distributed at different training stages. In the second setting, TDA techniques use checkpoints from 10 different models trained with varying randomness sources. Ensembling attribution scores across models can enhance TDA performance. We evaluate the Linear Data Modeling Score, LDS, across different data sampling ratios. source consistently outperforms baseline methods in achieving higher LDS values, except when removing a single training data point. Using multiple segments with source typically improves LDS performance. The relative rankings of TDA techniques remain consistent across various data sampling ratios. In scenarios where implicit differentiation-based methods face challenges, such as non-converged models with few update iterations or models trained sequentially with different datasets, source demonstrates advantages over these methods in terms of LDS performance. Source performs well against baseline techniques in these scenarios, even outperforming ensembled versions of competing methods. Section Summary. In this section, we conduct experiments to address two main questions. Firstly, we compare source with existing TDA techniques using linear data modeling score, LDS, and subset removal counterfactual evaluation. Secondly, we explore if source can aid data attribution in scenarios where implicit differentiation-based methods struggle, such as with models trained in multiple stages or not yet converged. Our experiments cover various machine learning tasks like regression, image classification, text classification, and language modeling, comparing source against REPSIM, TRACIN, track, and influence functions, if, with the EK-FAC approximation, showcasing source's superior performance in most cases, especially in scenarios where implicit differentiation-based methods face challenges. Section: TDA for non-converged models. In this section, we assess the effectiveness of TDA techniques for models that have not fully converged. We conduct experiments using modified versions of the concrete and fashion MNIST datasets, where we corrupt target values or relabel a portion of the data points. The models are trained for only 3 epochs to prevent overfitting, and we use intermediate checkpoints at the end of each epoch for analysis. In our experiments, we find that TRACIN outperforms influence functions on both tasks, although source achieves the best performance overall due to its independence from the final weight's optimality. We also demonstrate that this trend holds true for linear models in a separate experiment. Furthermore, we explore TDA for sequentially trained models, where a model is first trained on one dataset and then on another. We use test examples from the second dataset to analyze the impact of the first dataset on the final model behavior. This sequential training setup presents challenges due to catastrophic forgetting. For methods like track and if that do not distinguish between training stages, we combine data from both stages for analysis. Our experiments on rotated MNIST and PACS datasets show that source performs well in continual learning scenarios, even when faced with multiple data distributions. Additionally, we investigate subset removal counterfactual evaluation as another method to evaluate TDA techniques. This approach examines how model behavior changes when highly influential data points are removed based on different attribution techniques. Effective attribution methods should pinpoint data points whose removal significantly alters model behavior. Our experiments on various classification tasks demonstrate that source excels in identifying influential data points that lead to misclassification, especially in challenging scenarios where implicit differentiation-based methods struggle.